Come back to the dark with me tonight. There is a star you have learned to call the sun. It rises every morning steady and white and silent. It has burned for 4.5 billion years. It will burn for 5 billion more. And then it will die. Tonight, I want to tell you the whole story of that death. How a star is born from a cloud that fell into itself, how it burns in perfect balance for billions of years, and how it ends. And the quiet truth waiting at the end, that the carbon in your body and the iron in your blood were made inside stars that died long before the sun, so that you could be here, listening, tonight. If this feels like a place you'd like to return to, leave a small light behind, a like, a subscription, so others can find their way here too. Lower the lights now. Put on your headphones. Let the weight of the day fall away. We're going to follow a single thread tonight, one that stretches across billions of years and ends, quietly, in the atoms that make up your hand, your breath, the room around you. The stars are not eternal. Every one of them is keeping time. And tonight we'll walk through that time together, from beginning to end. I have been mapping these distant places for longer than I can remember. I am the cartographer of the dark. And tonight we are walking together through the lives and deaths of stars, the same fires that forged every atom in your body. Every star you see tonight is dying. Some just take billions of years to do it. The sun is approximately 4.5 billion years old. Measured not by guesswork but by the oldest grains of solid matter found drifting in the solar system. Tiny crystals of calcium and aluminium that condensed when the nebula first began to collapse. It has roughly 5 billion years remaining. It is, in the most literal sense, halfway through its life. Not young, not old, middle-aged, burning steadily, holding itself together by a balance so precise that if either side faltered for even a moment, the star would either collapse or blow itself apart. But the clock is running. Every star in the sky has one. The timer started the moment fusion ignited in the core, the moment hydrogen atoms first collided with enough force to merge and release light. From that instant forward, the star began to spend the only currency it has: fuel. And when the fuel runs out, the star changes. How it changes depends entirely on how much mass it was born with. A star 10 times the mass of the sun will burn through its entire reserve in only a few million years, dying young and violently. A star 1/10 the mass of the sun will sip its hydrogen so slowly it could burn for hundreds of billions of years, longer than the universe has existed so far. The sun sits somewhere in between, steady, predictable, mortal. And it is not alone. If you could see the clocks ticking inside every point of light scattered across the night sky, you would see a galaxy full of countdowns, each one set to a different span, each one moving toward a different kind of ending. Some stars will fade quietly, others will detonate. A few will collapse so completely that not even light can climb back out. But all of them, every single one, will end. The question is not whether, the question is when, and how, and what they leave behind. The way a star dies is not random. It follows rules written into the fabric of matter itself. Rules about pressure and temperature, and the behavior of atoms under gravity's grip. The smallest stars will cool slowly over trillions of years, their embers drifting through the dark long after galaxies have dissolved. The largest will ignite a cascade of fusion so extreme that within seconds the core will collapse, and the outer layers will explode outward at a fraction of the speed of light. The sun will do neither. It will swell, glow red, shed its outer layers in a glowing shell, and leave behind a core no larger than the Earth but dense enough that a single cubic centimeter weighs about as much as a car. This is not tragedy, this is continuation. Because the atoms released by a dying star do not vanish, They drift, they cool, they mix with clouds of hydrogen, left over from the beginning of the universe, and eventually, in some distant region of space, they collapse again. A new star forms. New planets condense from the disk, and on at least one of those planets, those atoms become part of something else. Oceans. Atmosphere. Life. You are made of dead stars. Not metaphorically. Literally. The carbon in your cells, the oxygen you are breathing right now, the calcium in your bones, the iron in your blood, every atom heavier than hydrogen, passed through the interior of a star that died before the sun was born. Some of those atoms were forged slowly, in the steady burn of a star like the sun. Others were made in the final seconds of a supernova, in temperatures so extreme that nuclei collided and fused into elements that cannot form any other way. And the sun, which gave you warmth and light and made this planet habitable, is halfway through the same journey. 5 billion years from now, the hydrogen at its core will be gone. The fusion that has held the sun in balance for nearly 5 billion years will stop. The core will contract. The outer layers will swell. The sun will become a red giant, its surface cooling and reddening, even as its radius grows to swallow the inner planets. Mercury will be consumed. Venus will follow. Whether Earth survives is still debated. Most models predict that it too will be engulfed, dragged inward by tidal forces, even as the sun loses mass and the orbits of the planets drift outward. A few models allow for a narrow escape. What every model agrees on is this: long before the sun's surface reaches Earth's orbit, the oceans will have boiled away, the atmosphere stripped, the surface baked sterile. But the sun will not stop there. For a brief time, by the standards of stars, the dying sun will create one of the most beautiful structures in the cosmos. A planetary nebula, named not because it has anything to do with planets, but because early astronomers thought the glowing disks resembled Uranus. They are nothing of the sort. They are shells of gas, lit from within by the exposed core of the star, glowing in blues and greens and reds stretched across light years. The gas expands. The light fades. Within about 50,000 years, the nebula disperses, and all that remains is the core, a white dwarf, roughly the size of the Earth, roughly the mass of the Sun, compressed so tightly that a teaspoon of its matter would weigh several tons. It will not burn, it will not fuse, it will simply sit in space, radiating the heat it accumulated over billions of years, cooling slowly, degree by degree, across timescales so long they make the entire history of human civilization look like the blink of an eye. The oldest white dwarfs known have been cooling for 11 or 12 billion years. They have dimmed to a faint red glow, their surfaces cooled to temperatures around 4,000 degrees, still hot by human standards, but cold for a star. And they will keep cooling. In theory, a white dwarf will eventually become a black dwarf, a cold, dark crystal of carbon and oxygen, emitting no light, no heat, drifting invisibly through the void. But the cooling required takes at least 100 million billion years, far longer than the current age of the universe. No black dwarf exists anywhere in the cosmos today. The universe is not old enough. This is the fate of every star born with a mass similar to the Sun: quiet, slow, a long fade into darkness. But not all stars go quietly. The stars born with 10, 20, 30 times the mass of the Sun follow a different path entirely. They burn hotter, faster, wilder. They fuse helium into carbon, carbon into oxygen, oxygen into neon, neon into silicon, silicon into iron, and iron is where fusion ends. Iron cannot release energy when it fuses. So when the core fills with iron, the fire stops. Gravity wins. The core collapses in less than a second. The outer layers rebound in a shockwave, traveling at tens of thousands of kilometers per second, a supernova. For a few days, a single dying star can outshine every other star in its galaxy combined. What remains depends on the mass of the core. If the remnant is light enough, it freezes into a neutron star, matter so dense that a sugar cube of it would weigh 1 billion tons. If the core is heavier still, it collapses past any known stopping point. A black hole forms, and in doing so they give everything back. Lower the lights, put on your headphones, because the story of stellar death is not one story, it is many. And the next chapter belongs to the stars that were born from clouds of gas and dust, hundreds of light years across, that fell slowly into themselves. I wonder where you are tonight. What part of the world is listening in the dark? The stars above you are not the same ones someone else is watching, halfway around the planet. If you feel like it, leave your city below. A star begins as a cloud that forgot to stay scattered. Somewhere between the arms of a spiral galaxy, a region of gas and dust drifts through space, spread across hundreds of light years. Most of it is hydrogen, the simplest atom, the oldest ingredient. There is helium. There are trace amounts of heavier elements left behind by earlier stars that lived and died before this cloud ever formed. For millions of years, nothing happens. The cloud simply drifts, a diffuse whisper of matter, so thin that a human standing inside it would see nothing but darkness and a scattering of distant stars. Then, somewhere within it, the balance tips. Perhaps a nearby supernova sends a shockwave through the region. Perhaps the cloud simply grows dense enough, molecule by molecule, until gravity begins to notice. Whatever the trigger, a small pocket of the cloud begins to collapse. Slowly at first, then faster. Gravity pulls inward, and there is nothing to resist it. The cloud has no internal pressure, no heat, no light, it only has mass. And mass obeys one law above all others. It falls toward itself. As the cloud contracts, something changes. The atoms that were once separated by light years are now crowding into a smaller and smaller volume. They collide, they jostle, their motion generates heat. The center of the collapsing cloud begins to warm. What was once a cold, invisible drift of hydrogen becomes a glowing knot of gas. This is not yet a star. It is a protostar, a candidate, a promise. It shines not because it is burning fuel, but because it is falling. The glow comes from gravitational energy, the slow conversion of motion into heat as the cloud crushes itself inward. The collapse is not uniform. The cloud rotates, slowly at first, then faster as it shrinks. The center continues to fall straight down, but the outer material begins to spiral. It forms a disk, a flat plane of gas and dust, orbiting the growing protostar at the center. This disk is not a side effect, it is the future. Within it, grains of dust will stick together, clump by clump, building pebbles, then boulders, then planetesimals, then worlds. The same material that builds the star also builds the planets that will one day orbit it. Our solar system formed this way, approximately 4.5 billion years ago, from a single collapsing cloud. The Sun and the Earth are siblings, born from the same nebula, separated only by the accident of distance and the physics of rotation. The iron core of the Earth, the water in its oceans, the nitrogen in its atmosphere, all of it came from that disk, and the disk came from the cloud. And the cloud came from the remnants of stars that died before the Sun ever existed. For hundreds of thousands of years, the protostar continues to collapse. Its core grows hotter. The outer layers, still falling inward, feed the disk, which feeds the core. The temperature at the center climbs. 10,000 degrees, 100,000, a million. The pressure becomes immense. Atoms are stripped of their electrons, leaving bare nuclei careening through a sea of charged particles. This is plasma now, not gas. The core is a furnace, but it is not yet burning. It is simply hot, compressed, waiting. Then, when the core temperature reaches approximately 10 million degrees, something extraordinary happens. Hydrogen nuclei, which have been colliding and bouncing apart for millennia, begin to stick together. The heat and pressure are finally enough to overcome the electromagnetic repulsion between positively charged protons. They fuse. Two hydrogen nuclei become one helium nucleus. In the process, a tiny fraction of their mass is converted directly into energy. The energy released by a single fusion event is minuscule. But there are trillions upon trillions of hydrogen atoms in the core, and they are fusing billions of times per second. The protostar ignites. Fusion begins. Light pours outward from the core, carried by photons that will take tens of thousands of years to fight their way to the surface, scattering and absorbing and re-emitting through layer after layer of dense plasma. The outward pressure generated by fusion balances the inward pull of gravity. The collapse stops. The star stabilizes. What was a cloud is now a sphere of light, held in equilibrium by two opposing forces, neither of which will yield for billions of years. This is how a star is born. Not in an instant, but across an unimaginable span of time. Not from fire, but from falling. The cloud collapses because gravity insists. The core heats because motion becomes temperature. Fusion ignites because pressure and heat cross a threshold that cannot be uncrossed. There is no intention, no design. Only physics, patient and inexorable, turning a whisper of hydrogen into a furnace that will burn for longer than any human civilization has existed. The nebula that gave birth to the sun no longer exists. It dispersed long ago, its materials scattered into stars and planets, and the thin gas between them. But across the galaxy, the process continues. In the Orion Nebula, approximately 1,500 light-years away, new stars are forming right now. The nebula glows pink and red, lit by the ultraviolet light of young stars already born. Inside its densest regions, protostars are collapsing, their cores warming, their disks forming. Some of them will ignite within the next few 100,000 years. Others are already burning, hidden inside cocoons of dust too thick for visible light to escape. The Eagle Nebula, 7,000 light-years distant, holds columns of gas and dust so dense they have their own name, the Pillars of Creation. Inside those pillars, stars are being born. The pillars themselves are being eroded by the light of nearby young stars, their surfaces boiling away into space. In a few million years the pillars will be gone, and the stars forming inside them will emerge, newborn and brilliant, adding their light to the galaxy. Each of these clouds follows the same script: collapse, heating, ignition. The details vary. A cloud with more mass collapses faster and ignites a hotter, brighter star. A cloud with less mass takes longer and produces a cooler, dimmer ember that will burn for hundreds of billions of years. But the pattern holds. Gravity pulls. Pressure rises. Fusion begins. A star is born. The ignition itself is not instantaneous. There is no single moment when the star switches on. Fusion begins in the very center of the core, in a region no larger than the Earth. Then it spreads outward, degree by degree, as the surrounding layers heat and compress. The protostar flickers, it brightens, it settles. Stellar winds begin to blow outward, clearing the inner disk, carving out a gap around the newborn star. The remaining material either falls into the star, coalesces into planets, or is blown away into space. Eventually, the star reaches equilibrium. The core is hot enough to sustain steady fusion. The outer layers are stable. The disk has either formed planets or dispersed. The star enters the main sequence, the long middle stretch of its life, the phase defined not by change but by constancy. For stars like the Sun, this phase lasts approximately 10 billion years. For more massive stars, it lasts only millions. For the smallest red dwarfs, it lasts hundreds of billions of years, longer than the current age of the universe. But all of that comes later. For now, the cloud has fallen. The core has ignited. The fire has caught. A new point of light has appeared in the galaxy, one that was not there a million years ago, one that will burn for billions of years to come. Somewhere in the disk around it, dust grains are beginning to stick together. Somewhere farther out, ice and rock are accumulating in the cold. The star has been born. And in its birth, it has seeded the possibility of worlds. For billions of years, two forces hold the star in perfect balance. Gravity pulls inward, trying to crush everything toward the center. Fusion pushes outward, releasing energy from the core, where hydrogen atoms are fusing into helium, 4 at a time, over and over, trillions upon trillions of reactions every second. Neither force wins. The star simply burns. This is the main sequence. This is the long middle. This is where most stars spend most of their lives. The Sun has been doing this for roughly 4.5 billion years. It will continue doing this for another 5 billion. The same dance, the same balance, the same steady outpouring of light. The hydrogen at the core is vast but not infinite. The clock is ticking, but slowly. So slowly that entire civilizations could rise and fall in the time it takes the fuel gauge to move. The core is a sphere of plasma roughly a quarter of the Sun's radius, where temperatures reach 15 million degrees. Here, in this compressed furnace, hydrogen nuclei move fast enough to overcome the force that normally keeps them apart. They collide. They fuse. 4 hydrogen nuclei become 1 helium nucleus, and in the process a tiny fraction of their mass becomes energy. Not much, less than 1%. But when you multiply that fraction by the sheer number of reactions happening every second, the output is staggering. Every second, the Sun converts roughly 4 million tons of mass into energy. 4 million tons, simply ceasing to exist as matter and becoming light. This has been happening every second for 4.5 billion years, and the Sun has barely noticed. It has lost less than 0.1% of its total mass. The reservoir is deep. But not all stars burn at the same pace. A star 10 times the mass of the Sun burns hotter, brighter, faster. Its core is a furnace under greater pressure. Gravity squeezes harder. Fusion accelerates. The hydrogen there fuses so quickly that the star exhausts its fuel not in billions of years, but in tens of millions. A star 40 times the mass of the Sun might last only a few million years on the main sequence. Brilliant and brief. These massive stars are rare, but they dominate the night sky. Most of the brightest stars you can see without a telescope are young, massive, and burning themselves out at a reckless pace. Rigel, Deneb, Spica. Each one is racing through its hydrogen supply, pouring out hundreds or thousands of times the light of the Sun, destined to die long before our Sun even begins to swell. At the other end of the spectrum are the red dwarfs, small, dim, miserly with their fuel. A star 1/5 the mass of the Sun burns so slowly that it could remain on the main sequence for hundreds of billions of years, longer than the current age of the universe. These stars are faint, cool, patient. Most of them are invisible to the naked eye. but they are everywhere. They make up roughly 3/4 of all the stars in the galaxy. If you could watch one of these stars from beginning to end, you would need to wait longer than all of recorded history, multiplied by a factor so large it loses meaning. The universe itself is not old enough for a single red dwarf to have completed its main sequence lifetime. Not one. Every red dwarf that has ever formed is still burning its original hydrogen. They are still in the long middle, and will be for hundreds of billions of years to come. The paradox is this: the more fuel a star has, the faster it burns through it. Mass is not a gift of longevity, it is a sentence of speed. And so the night sky is filled with stars at different points along this spectrum. Some are young and wasteful, some are old and patient. But all of them, no matter their mass, are doing the same thing. They are converting hydrogen into helium. They are holding themselves up against their own gravity. They are buying time. The balance is delicate. If fusion were to slow, even slightly, gravity would begin to win. The core would contract. The star would shrink. But contraction heats the core, which speeds up fusion, which pushes back against gravity, which restores the balance. The star regulates itself. This feedback loop is what makes a main sequence star stable. It is not a static object. It is a negotiation, constantly adjusting, constantly responding. The core temperature rises or falls by tiny fractions. The fusion rate ticks up or down. The radius expands or contracts by the smallest margins. And the star remains for all practical purposes unchanged. We see this stability in the Sun. Its brightness varies by less than 0.1% over the course of a solar cycle. Its radius changes by fractions of a kilometer. For a sphere more than 1,000,000 kilometers across, this is essentially motionless. The Sun you see today is the same Sun that shone on the first forests, the first oceans, the first single-celled organisms floating in warm water 3.5 billion years ago. The light that warmed the skin of the last dinosaur came from the same process, the same core, governed by the same physics. But stability is not permanence. Hydrogen is being consumed. Helium is accumulating in the core is not mixing with the outer layers. The helium simply builds up, inert, waiting. Slowly, over billions of years, the composition of the core shifts. The percentage of hydrogen drops. The percentage of helium rises. The star is changing, but so gradually that the change is invisible. The Sun today has slightly less hydrogen in its core than it did 1 billion years ago. 1 billion years from now, it will have slightly less still. The trend is slow, but it is irreversible. For now, the Sun is still in balance. The hydrogen is still plentiful. The fusion continues. The light streams outward, 8 minutes and 20 seconds to Earth, then onward into the dark, carrying energy that began as mass in the core. The energy does not leave the core quickly. A photon produced in the heart of the Sun does not travel in a straight line to the surface. It collides with atoms. It is absorbed and re-emitted, scattered in random directions, again and again, millions of times. The journey from core to surface can take tens of thousands of years. By the time the light reaches your eyes, it is older than human civilization. Elsewhere in the galaxy, other stars are further along. Some have already exhausted the hydrogen in their cores. The balance has tipped. Fusion has slowed, then stopped at the center. Gravity has begun to win. These stars are no longer on the main sequence. They have moved on to the next phase. Their long middle is over. And some stars, the red dwarfs scattered throughout the spiral arms, have not even reached their midpoint yet. They are still in the early chapters of a story that will outlast everything currently alive. They will burn long after the Sun has died. Long after the Milky Way and Andromeda have merged. Long after the last new stars have formed in the universe. They will be the last lights left on, burning in a cosmos that has grown cold and dark and empty. But that is far ahead. Unimaginably far. For now, the main sequence continues. Hydrogen fuses. Helium accumulates. The balance holds. The stars burn steadily, predictably, in a rhythm set by their mass and nothing else. They are clocks. They are forges. They are engines of light, running on the simplest fuel in the universe, the first element, the atom that was born in the first 3 minutes after the beginning. And when you look up at the night sky, almost every star you see is in this phase. The long middle. The hydrogen-burning years. The era of balance. They are not being born. They are not dying. They are simply existing, steadily, in the only way a star knows how. The Sun is one of them. A middle-aged star, halfway through its allotted time, burning at a rate that will keep the Earth warm for billions of years to come. Not the brightest. Not the dimmest. Not the largest or the smallest, just one more point of light, holding itself together, fusing hydrogen, radiating energy into the void. And for now, that is enough. When the hydrogen runs out at the center, the fire does not die, it moves. The core, starved of fuel, begins to contract. Gravity, unopposed now by fusion pressure, pulls the spent helium inward. The compression heats the core again, and the heat floods outward into the layers above. Those outer layers, flooded with energy from below, begin to expand. Slowly at first, then faster. The star swells. What was once a point of white light becomes a vast red cloud. This is the red giant phase. The surface, stretched across an enormous volume, cools. The light shifts from white to orange to deep red. But the star itself is not cooling. The core is hotter than it has ever been. The fire has simply migrated to a shell surrounding the core, burning hydrogen in a thin layer, while the helium ash at the center waits for its own ignition. The expansion is difficult to grasp in human terms. A star the size of the Sun, a sphere that could hold more than 1 million Earths, grows until it could swallow the orbits of the planets nearest to it. The radius stretches outward, past the orbit of Mercury, past Venus, perhaps even past the orbit of Earth itself. The star becomes a red giant not because it is dying but because it is rearranging itself for the next act. In approximately 5 billion years the Sun will enter this phase. The transformation will take millions of years, but the outcome is already written in the physics of its mass and composition. The Sun will swell. Its outer atmosphere will extend to somewhere between the orbit of Earth and the orbit of Mars. The inner planets will not survive. Mercury will be swallowed. That much is certain. The smallest planet, already scorched and airless, will spiral inward through the expanding solar atmosphere, its orbit decaying as it drags through thickening gas. Eventually it will vaporize. Its atoms, mixed into the outer envelope of the dying Sun. Venus will follow. The second planet, shrouded now in sulfuric acid clouds and crushing heat, will meet the same fate. The Sun's outer layers will reach it, engulf it, and erase it. Earth's fate is less certain. Whether our world survives depends on a race between two processes. As the Sun loses mass through stellar winds, the gravitational grip on the planets weakens. Orbits drift outward. At the same time, the Sun's outer atmosphere expands. creating drag on anything moving through it. Tidal forces pull the planets inward, even as the loss of solar mass pushes them outward. The models do not agree. Some predict Earth will drift just far enough to escape. Most predict it will not. What the models do agree on is this: long before the question of engulfment is decided, the oceans will be gone. As the sun brightens during its final million years on the main sequence, the surface temperature of the Earth will rise. The oceans will evaporate. The atmosphere will thicken with steam, trapping more heat, accelerating the loss. Within a billion years, perhaps less, Earth will be a dry, lifeless rock. Whether that rock is later consumed by the expanding sun or left to orbit a white dwarf in silence is a detail that will matter to no one. The red giant phase is not a stable state, it is a transition. The star is buying time, burning hydrogen in a shell, while the core continues to contract and heat. For a star like the Sun, this phase lasts only a few 100 million years. For more massive stars, the progression is faster. For the smallest stars, red dwarfs that burn their hydrogen so slowly they have not yet had time to leave the main sequence in the entire history of the universe, the red giant phase is still theoretical, a future so distant it has never been observed. But for stars of the Sun's mass, the red giant is the beginning of the end. The core continues to heat as it contracts. Eventually, if the core reaches a temperature of about 100 million degrees, helium itself begins to fuse. 3 helium nuclei combine to form carbon. The process releases energy. The core, briefly, stabilizes again. This is called the helium flash in stars like the Sun, a runaway ignition that lasts only seconds but releases as much energy as the entire galaxy for that brief moment. The star does not explode. The energy is absorbed by the dense core. But the structure changes. The outer envelope contracts slightly. The star becomes smaller, less luminous, though still far larger and brighter than it was during its main sequence life. This is a temporary reprieve. Helium burning lasts only a few tens of millions of years. When the helium runs out, the cycle repeats. The core contracts again. The outer layers expand again. The star becomes a red giant for a second time, larger and more luminous than before. The envelope grows unstable. Stellar winds begin to strip away the outer layers. The core, now composed mostly of carbon and oxygen, cannot ignite further fusion. The temperature is not high enough. The mass is not sufficient. For stars like the Sun, fusion ends here. In more massive stars, the story continues. The core can reach higher temperatures. Carbon fuses into neon and magnesium. Oxygen fuses into silicon and sulfur. Silicon fuses into iron. Each stage burns faster than the last. But for the Sun, the red giant phase is the final act of fusion. What comes next is not fire. It is light without heat, structure without energy. The long, slow dimming of a core that has nothing left to burn. The red giant is not a tragedy. It is a transformation. The outer layers, rich with carbon and oxygen forged during helium burning, will be returned to space. The light from the swollen star will illuminate the gas clouds around it. The core will remain, compressed and hot, a white dwarf waiting at the center of a glowing shell. But that is the next rung. For now, the star is simply vast. Red, cooling at the surface, burning in a shell, expanding into the space where its planets once orbited. You can see red giants in the night sky. Betelgeuse, in the constellation Orion, is one of the most familiar. It is a red supergiant, far more massive than the Sun. But the principle is the same. The core has exhausted its hydrogen. The outer layers have swelled. The star is hundreds of times larger than it was during its main sequence life. It will not remain this way. In a few 100,000 years, perhaps less, it will explode. But for now, it hangs in the winter sky, a red ember among white points, a star in transition. Aldebaran, the Eye of Taurus, is another. A red giant closer in mass to the Sun, though still more massive. It has left the main sequence. Its core is fusing helium. Its outer layers glow orange-red. In a telescope, the color is unmistakable. It is not the white of a young star or the blue of a massive one. It is the color of a star that has begun to let go. The red giant phase is brief, but it is also inevitable. Every star that burns hydrogen will eventually exhaust it. Every star will face the choice between contraction and expansion, between compressing the core and releasing the envelope. The mass of the star determines how many times this cycle repeats, how many elements are forged, how the end arrives. But the red giant is always part of the sequence. It is the moment when the fire reaches the surface, when the light changes color, when the star becomes something it has never been before. And when the sun swells, 5 billion years from now, there will be no one here to see it. The Earth, if it still exists, will be a cinder. The outer planets will drift in the light of a star that has grown large enough to fill half the sky from the orbit of Jupiter. The red glow will reach across the solar system. The helium core will burn, the hydrogen shell will feed it, and the sun, for a brief time by the measure of stars, will be larger and brighter than it has ever been. Then the helium will run out. The winds will begin, and the long goodbye will start. The outer layers of the star begin to lift away. Not violently, but steadily, like breath leaving a body that no longer needs it. The core beneath has contracted into something small and fierce and impossibly hot, no larger than the Earth, but radiating ultraviolet light so intense it strips electrons from atoms light-years distant. The envelope that once stretched halfway to the orbit of Mars is now drifting outward, expanding into the surrounding darkness at tens of kilometers per second. The ultraviolet flood from the exposed core catches the gas as it travels, ionizing it, lighting it from within. What forms is one of the most beautiful structures in the cosmos. A glowing shell of gas lit by the dying core at its center. Blues and greens and reds stretched across distances that would take light years to cross. The colors are not arbitrary. Oxygen glows green and blue-green. Hydrogen glows red. Nitrogen adds deep crimson threads. Each element fluoresces at its own wavelength, painting the nebula in layers of spectral light. The result is something that looks almost deliberately composed, as though the universe had turned for a moment to art. These are called planetary nebulae, though they were named for their resemblance to planets seen through early telescopes. They are nothing of the sort. They are the shed skin of a star, fluorescing in the radiation of what remains beneath. Each one is different. Some are symmetrical, layered like an onion or a series of nested shells. Others are chaotic, threaded with filaments and knots where the gas has bunched and twisted in magnetic fields. The Cat's Eye Nebula, the Helix, the Ring, the Dumbbell, the Eskimo, the Butterfly. Each one a monument to a star that spent billions of years burning hydrogen in equilibrium, and then, at the end, let go. The light show is brief by cosmic standards. Only about 50,000 years. Then the gas disperses into the surrounding interstellar medium, mixing with clouds of hydrogen and dust, seeding them with carbon and nitrogen and oxygen. The glow fades. The nebula becomes invisible, its atoms absorbed into the raw material from which the next generation of stars will form. What remains at the center is the core. A sphere roughly the size of the Earth but with the mass of the Sun compressed into it. This is a white dwarf. The matter inside is so dense that a single cubic centimeter weighs roughly a ton. A teaspoon of it, if you could somehow lift it, would weigh about 5 tons. The atoms are not destroyed, they are crushed together until the electrons are stripped away and packed into the spaces between nuclei. The material behaves more like a metal than a gas, even though the surface temperature can exceed 100,000 degrees. It is matter in a state that does not exist anywhere on Earth, held together by forces that operate only at extremes. There is no fusion happening inside a white dwarf. No fire. The core is composed mostly of carbon and oxygen, the ash left over from helium burning during the red giant phase. It glows only because it is hot, radiating away the thermal energy accumulated over billions of years of nuclear reactions. It is not a star in the way we usually think of stars. It is a remnant, a memory held in matter. When the Sun dies, it will shed approximately 4/10 of its mass in stellar winds and the planetary nebula phase. What is left will be a white dwarf of about 6/10 of a solar mass, glowing at the center of an expanding shell of gas that will, for a few tens of thousands of years, be visible from distances of thousands of light years. Then, the shell will fade. The white dwarf will remain. It will sit alone, glowing white-hot at first, then yellow, then red, then dimmer still. There will be no planets left to warm, no orbits to anchor, just the core, cooling. The structure of a white dwarf is unlike anything you encounter in everyday matter. The electrons inside are packed so tightly that quantum mechanics takes over. They obey what is called electron degeneracy pressure. This is not thermal pressure, the kind that comes from heat and the motion of particles. It is a pressure that arises purely from the fact that electrons cannot occupy the same quantum state. They push back against gravity, not because they are moving fast, but because there is simply no room left to compress them further. This pressure does not depend on temperature. A white dwarf could cool to near absolute zero, and it would not collapse. It would simply sit there, inert, held up by the refusal of electrons to be squeezed any closer together. This is what prevents the white dwarf from collapsing into something denser. For stars like the Sun, electron degeneracy is enough. The equilibrium is stable. The object will persist, unchanged in size, for trillions of years. But it will not stay hot. Heat leaks away. Slowly at first, then more slowly still, as the surface temperature drops and the rate of radiation decreases. The white dwarf cools through a sequence of colors. White, to yellow, to red, to infrared. Eventually, in theory, it becomes what is called a black dwarf. A cold, dark cinder of carbon and oxygen, emitting no light and no heat. Just mass. Just gravity. A fossil of a star. But no black dwarf exists anywhere in the universe today. The universe is not old enough. Not even close. The cooling timescale required is at least 100 million billion years. Vastly longer than the 13.8 billion years that have passed since the beginning. The oldest white dwarfs we have found, relics from the earliest generations of stars, have cooled to temperatures around 4,000 degrees, still glowing faintly in the infrared, still warm enough to be detected. They have been cooling for more than 11 billion years, and they are not even halfway to becoming black dwarfs. They will continue cooling for spans of time so long that the phrase "the future" begins to lose meaning. So when we speak of the final fate of the Sun, we are speaking of something that will not happen for an almost unimaginable span of time. The planetary nebula will disperse within 50,000 years of its formation. The white dwarf will cool over timescales 1 million times longer than the current age of the universe. Civilizations could rise and fall on worlds orbiting other stars. Galaxies could collide and merge. Stars could be born, live and die. The white dwarf will still be there, dimming by imperceptible degrees, waiting for a future so distant that even the concept of waiting seems inadequate. There is something quietly persistent about a white dwarf. It does not burn, it does not explode, it does not collapse into something stranger, it simply is. It holds its shape against the pull of its own gravity, through a principle of quantum mechanics that has nothing to do with temperature, or fuel, or time. It is patient in a way that only dead things can be patient, and it will outlast nearly everything else in the universe that we can see tonight. The Sun will become one of these. In about 5 billion years, after the red giant phase, after the shedding of the outer envelope, after the brief brilliance of the planetary nebula, the core will settle into this state. It will be alone. The nebula will have faded into invisibility. The planets, if any remain, will be distant, frozen and dark. The white dwarf will glow softly in the darkness, a pinpoint of light where once there was a furnace that warmed oceans and lit skies and made shadows on the surface of worlds. And then, over spans of time longer than the current age of the universe, it will cool. Degree by degree, century by century, eon by eon, until the light is gone. This is not a violent end. It is not a catastrophe. It is simply the way a star like the Sun completes its arc. The hydrogen runs out. The core contracts. The envelope expands and then lifts away, ionized and glowing. The core cools. And what is left becomes part of the long, quiet population of white dwarfs that will eventually fill the galaxy, glowing faintly at first, then not at all, drifting through the dark like embers from a fire that burned for billions of years, and then, at last, went out. The carbon and oxygen locked inside will remain, compressed and inert, a monument to the equilibrium that once held gravity and fusion in balance. The nebula, meanwhile, will have mixed back into the interstellar medium, its atoms ready to collapse again, to ignite again, to become part of the next star, the next planet, the next breath. A star 10 times the mass of the Sun does not go quietly. 20 times. 30, 40. These giants burn hotter, faster, wilder than anything we have watched so far. Where a star like the Sun takes billions of years to exhaust its hydrogen, these massive stars race through their fuel in mere millions of years. They live fast. They die young. And when the hydrogen runs out, they do not stop. They keep burning. The core contracts. The temperature climbs. Helium begins to fuse into carbon. The star has crossed a threshold. It is no longer burning a single fuel in a single way. It is burning whatever it can, in whatever shell is hot enough to sustain the reaction. Carbon fuses into oxygen, oxygen into neon, neon into magnesium, magnesium into silicon. Each stage burns faster than the last. Each new element requires higher temperatures, more pressure, more desperate conditions to ignite. The star becomes a layered structure, shells of different burning reactions stacked one inside the other, like the rings of a tree, each one counting down toward the same inevitable end. Hydrogen burning in the outermost shell, helium deeper in, carbon below that, oxygen, silicon. And at the very center, in the hottest, densest region the star can create, silicon fuses into iron. Iron fills the core. A sphere of metal growing heavier by the second, atom by atom, deep inside a star that is still blazing across light years of space. The outer layers know nothing of what is happening below. They continue to shine. But the core is filling with iron, and iron is where fusion ends. Every element lighter than iron releases energy when it fuses. That energy is what holds the star up, what keeps gravity from collapsing everything inward. Fusion is not just the source of light, It is the star's skeleton. The outward pressure of fusion balances the inward pull of gravity, and that balance is what we call a star. But iron is different. Fusing iron does not release energy, it consumes it. Iron is the wall. The core fills with iron, and the fire that has burned for millions of years simply stops. There is no transition, no warning, no gradual dimming. The pressure that held the core open vanishes in an instant. The core, no longer supported by fusion, collapses. Not over centuries, not over years, not even over hours. In less than a second, a sphere of iron the size of the Earth compresses into a ball, perhaps 30 kilometers wide. The collapse is so violent, so sudden, that the core rebounds. It does not fall smoothly into some new equilibrium. It crashes inward and then snaps back, like a spring compressed past its limit. The rebound sends a shockwave tearing outward through the star. The outer layers, still falling inward under their own weight, meet the shockwave head-on. The star explodes. A core collapse supernova. For a few days, a single dying star can outshine every other star in its galaxy combined. The explosion releases energy equivalent to 10 to the 28th power in megatons, a figure so large it loses meaning until you frame it this way. The supernova emits as much energy in a week as the Sun will produce over its entire 10 billion year lifetime. If you could stand on a planet orbiting a neighboring star and look up at the moment of detonation, the supernova would cast shadows at noon. It would be visible in daylight. A new star brighter than anything else in the sky, where none had been before. Astronomers on Earth have watched supernovae flare in distant galaxies, brief points of light that appear, blaze, and fade over the course of weeks. Each one marks the death of a massive star, the collapse of an iron core, the moment when gravity wins and the star tears itself apart in response. We have catalogued thousands of them. Each one is a lighthouse, a beacon saying, here, in this galaxy, a star just ended. And for a moment, it was the brightest thing you could see. And then, slowly, the light fades. The explosion dims. The shockwave expands outward at a fraction of the speed of light, sweeping up gas and dust, carving a bubble in the interstellar medium that will glow for thousands of years. We call these structures supernova remnants. The Crab Nebula is one. A cloud of glowing filaments, still expanding, nearly 1,000 years after the star that made it exploded in the year 1062. Chinese astronomers recorded it. They called it a guest star. It was visible in daylight for 23 days. What remains at the center depends on what the core became in that final second of collapse. If the core is light enough, the collapse halts. The neutrons in the core, packed so tightly they are touching, resist being crushed any further. Quantum mechanics pushes back. The core freezes into something new, a neutron star. Matter so dense that a sugar cube of it would weigh 1 billion tons. A sphere perhaps 20 kilometers across, containing more mass than the Sun. The entire star, all its millions of years of fusion and light and wild burning, compressed into an object you could drive across in the time it takes to listen to a song. Neutron stars are not inert. Some of them spin. Some spin hundreds of times per second, their surfaces moving at a significant fraction of the speed of light. Some emit beams of radiation from their magnetic poles, sweeping across space like a lighthouse. We call those pulsars. They are clocks, perfectly regular, ticking faster than a hummingbird's heartbeat, the collapsed hearts of stars that died in violence and left behind only rhythm and spin. But if the core is heavier, if the mass that remains after the explosion exceeds a different threshold, the neutrons cannot hold. There is no known force, no quantum pressure, no structure in physics that can stop the collapse. The core keeps falling inward, past the neutron star threshold, past any stopping point we understand. It collapses beyond the reach of observation. The gravity becomes so intense that not even light can escape. A black hole, depending on the mass of what remains, the core becomes one or the other. A lighter remnant freezes into a neutron star. A heavier one collapses into a black hole. The dividing line is uncertain. It depends on mass, on rotation, on details still being measured. But the general shape is clear. A core of a few solar masses becomes a neutron star. A core heavier than that becomes a black hole. And the star that produces such a massive core must have been enormous to begin with. 30, 40, 50 times the mass of the Sun. Burning fast. Burning bright. Dying in a flash that briefly makes it the most luminous object in its corner of the universe. The supernova does not just mark the end of a star. It is also the moment when much of the periodic table is born. During the collapse and the explosion, conditions become so extreme that elements heavier than iron, elements that cannot be forged by normal fusion, are created in seconds. Gold, silver, platinum, uranium. All the heaviest elements are made in the chaos of a collapsing core, in the neutron-rich furnace of the explosion, or later in the collisions of neutron stars. The blast flings them outward into space, seeding the galaxy with the raw material for planets, for oceans, for bones and blood. Every atom of iron in your blood passed through a supernova. It was forged in the final moments of a massive star's life, in the core just before the collapse, and scattered into the void when the star exploded. Billions of years later, it drifted into a cloud of gas and dust that slowly fell into itself and became the Sun and the solar system. It gathered into a world. It cycled through stone and water and air and living things, and eventually it became part of you. The neutron star or black hole left behind does not fade. It does not cool like a white dwarf, radiating its heat into the dark. A neutron star can spin for millions of years, gradually slowing as it loses rotational energy, but it remains. A black hole simply persists, warping the space around it, invisible except for the way it bends light or pulls on nearby matter. These remnants are not like the quiet end awaiting the Sun. They are scars. Marks left by stars that burned so fiercely they could not die without tearing the fabric of space-time. And yet, in a way, they are no different from the glowing shell of gas that will one day surround the Sun's fading core. They are transformations. The star does not vanish. It changes. Its matter becomes something new, its energy spreads outward. The light from the supernova travels for millions of years, reaching worlds that will form long after the explosion. The elements it forged drift through the galaxy, mixing with clouds of hydrogen, waiting to collapse again, waiting to become the next generation. There is no waste. Only continuation. A massive star dies in a flash of light bright enough to be seen across the universe, and what it leaves behind is a kind of memory. A record that something enormous once burned here, that it fused hydrogen into helium, helium into carbon, carbon into iron, that it held itself together against its own gravity for millions of years, and that when it could hold no longer, it gave everything back. The supernova is not an ending. It is the moment when a star becomes the universe again. The carbon in your body was fused in the core of a star that died before the Sun was born. The calcium in your bones. The iron in your blood. Every atom heavier than hydrogen passed through the interior of a star at some point in the past. You are, in the most literal sense, made of dead stars. This is not poetry, it is physics. When the first stars formed, the universe contained only hydrogen and helium, left over from the Big Bang. Everything else had to be made. And the only place with enough heat and pressure to forge new elements was the core of a burning star. Inside a main sequence star, hydrogen fuses into helium. The temperature climbs. The pressure builds. When the hydrogen runs out, helium begins to fuse. Two helium nuclei collide and stick. Then another. Carbon forms. The reaction continues. Carbon fuses with helium to make oxygen. The star burns through its fuel in layers, building heavier and heavier elements as the core contracts and heats. Carbon, oxygen, neon, magnesium, silicon. Each stage burns faster than the last. Each one releases less energy. The star is not running out of fuel so much as running out of time. For a star like the Sun, the process stops at carbon and oxygen. The core never gets hot enough to go further. When the outer layers are blown away in a planetary nebula, what remains is a white dwarf, a sphere of carbon and oxygen roughly the size of Earth, cooling slowly in the dark. Those elements stay locked inside, waiting for the universe to grow cold around them. But for a massive star, the burning does not stop. The core keeps contracting. The temperature keeps rising. Carbon fuses into neon, neon into oxygen and magnesium, oxygen into silicon, silicon into iron. And then, suddenly, the fusion stops. Iron is the end of the line. Fusing iron does not release energy, it consumes it. The core, now filled with iron, can no longer support itself. Gravity wins. The core collapses in less than a second. The rebound is catastrophic. The outer layers of the star, still falling inward, slam into the rebounding core and explode outward at a fraction of the speed of light. A supernova. For a few days, the dying star outshines every other star in its galaxy combined. The energy released is staggering, approximately 10 to the 28th megatons. And in that explosion, in the heat and chaos and violence of the collapse, elements heavier than iron are forged: gold, silver, platinum, uranium. Elements that require more energy to make than fusion can provide. They are created in the shockwave, in the neutron-rich environment of the collapsing core, in the moments when a massive star tears itself apart. Some are forged in the supernova itself. Others are made later, when two neutron stars spiral into each other and merge, releasing a flood of neutrons that slam into lighter nuclei and build them up, one at a time, into the heaviest elements in the periodic table. Every element that is not hydrogen or helium was made this way. Inside a star, or in the death of a star, or in the collision of two dead stars long after their light went out. The calcium in your bones was forged in the late stages of a massive star's life, in the layers surrounding the iron core, during the final centuries before the supernova. The iron in your blood was made in that core in the last moments before collapse, and scattered across light years when the star exploded. The oxygen you are breathing right now was fused from helium in a red giant, billions of years ago, and released into space when the star's outer layers drifted away. Almost everything you are made of came from a star that no longer exists. This is not a metaphor, it is a lineage. The atoms in your hand have their own history. They were born in fire. They drifted through space for millions of years, part of a cloud of gas and dust, until gravity pulled them together again. They became part of the nebula that collapsed to form the Sun and the solar system. Some ended up in the disk of material that would become Earth. Some were buried in the crust. Some were drawn up into the atmosphere, or dissolved in the ocean, or absorbed by a plant, or eaten by an animal, or passed down through generations of life until, eventually, they became you. You are not separate from the cosmos. You are a part of it. A temporary arrangement of elements that were forged in stellar cores and scattered by stellar winds and supernovae, gathered again by gravity, assembled into a planet, and then into life, and then into the specific collection of carbon and oxygen, and calcium and iron, that is reading these words right now. The universe does not make anything from scratch, it recycles. Every atom in your body has been somewhere else before. It has been part of a star, part of a cloud, part of a rock, part of the ocean, part of another living thing. You are made of borrowed material, on loan from the cosmos. And one day, the atoms that are currently you will be something else. They will return to the earth, or the air, or the water. They will drift, they will wait, and eventually they will become part of something new. The death of a star is not an ending, it is a transfer. The star gives everything it made back to the universe. The nebula it leaves behind becomes the raw material for the next generation. New stars, new planets, new chances for complexity to emerge. Every element heavier than helium in your body came from a dead star. Every breath you take contains oxygen that was fused in a red giant. Every bone in your body contains calcium that was forged in advanced burning stages and dispersed by a supernova. The iron that carries oxygen through your bloodstream was made in the collapsing core of a massive star, in the final second before it exploded. You are the continuation. The universe took what the stars made and built something new. It built planets, it built oceans, it built life, it built you. This is what stellar nuclear synthesis means. Not that stars make elements, but that stars make everything, including you. The theory was first proposed in the middle of the last century, refined and expanded in a landmark paper published in 1957. The framework that explains how every element is forged, where in the star each one forms, and how they are released into space. The periodic table is not arbitrary. Every element has a birthplace. The atoms in your hand and the atoms in a distant nebula share the same origin. You are made of dead stars. Not in some vague, poetic sense. In the most concrete, physical, traceable way. The carbon, the oxygen, the calcium, the iron. All of it stellar. All of it forged in fusion or in collapse, or in collision. All of it scattered. All of it gathered again. The stars do not die in vain. They die so that something else can begin, and you are part of what began. The hydrogen in your body is different. It is primordial. It was never inside a star. It came from the Big Bang itself, forged in the first few minutes of the universe's existence. But almost everything else, every atom with more than one proton in its nucleus, required a star. Required fusion. Required heat and pressure that only exists in stellar cores or in the violence of stellar death. The phosphorus in your DNA. The sulfur in your proteins. The nitrogen that makes up most of the air you breathe. All stellar. All forged in the interiors of stars that burned for millions or billions of years, and then gave everything back. When you look at the night sky, you are not looking at something separate from yourself. You are looking at your own origin. The light from those stars is the same process that made you. Fusion. The conversion of lighter elements into heavier ones. The slow, patient construction of complexity from simplicity. The stars made the elements. Gravity made the planets. Chemistry made life. And here you are, a collection of stellar debris organized into something that can think and feel and wonder where it came from. The answer is written in your bones, in your blood, in every breath. You came from the stars. The atoms that make you were forged in stellar furnaces, scattered across light years, and gathered again by gravity into this particular arrangement, in this particular moment. You are made of dead stars, and when the atoms that are currently you drift apart and return to the cosmos, they will carry that history forward. They will become part of something else. Another cloud, another star, another planet, another chance for the universe to look at itself and wonder. Nothing is wasted. Everything continues. The white dwarf is not dead. Not yet. It is dying. very slowly. It has no fuel left to burn, no hydrogen, no helium, no fusion of any kind, only heat. The heat left over from the billions of years it spent burning. And heat, eventually, leaves. A white dwarf radiates its stored warmth into the darkness of space. The process is measured not in years, not in millions of years, but in billions. The oldest white dwarfs we have found, scattered through the halo of our galaxy, have been cooling for approximately 11 to 13 billion years. They began their long fade when the universe itself was young, and today, after all that time, their surfaces still glow at temperatures around 4,000 degrees. Still hot enough to shine faintly in the infrared. Still warm, by any human measure. But the universe is patient. And the white dwarf has nowhere to go. Nothing left to do but wait. You can think of it as an ember. Not the flame, not the fire, but what remains when the fire is gone. It sits in the dark, giving off light it no longer has the means to replace. Slowly, degree by degree, century by century, it cools. There is no drama in this. No stellar wind strong enough to sculpt a nebula. No collapse. The white dwarf that once cast off its outer layers in a glowing shell now sits at the center of empty space, alone. The nebula dispersed long ago. The gas returned to the interstellar medium. What remains is only the core, a sphere roughly the size of Earth. A mass approaching that of the Sun. A density of roughly 1 ton per cubic centimeter. The electrons inside are packed so tightly they cannot move. They exist in what is called a degenerate state, held in place not by heat or chemical bonds, but by the quantum mechanical rule that says no two electrons can occupy the same state. It is this pressure, this refusal of matter to compress any further, that keeps the white dwarf from collapsing. Not fusion, not temperature. Just the stubbornness of quantum mechanics. And so it cools, the surface temperature drops from white hot to yellow, from yellow to orange, from orange to red. The light shifts down through the spectrum. Visible light gives way to infrared. Infrared fades toward radio. The white dwarf grows dimmer, fainter, harder to see against the background glow of the galaxy. If you could watch one for 1 billion years, you would see almost nothing. A slight dimming, perhaps. A shift in color. The surface temperature dropping from 5,000 degrees to 4,000, from 4,000 to 3. The process is glacial. There are no milestones, no events to mark the passage of time. Only the slow, inexorable loss of heat into the void. The galaxy is full of them. Tens of billions, perhaps hundreds of billions, depending on how you count. Most are invisible to the surveys we conduct. A few are still hot enough to glow faintly in the catalogs. Some orbit other stars, their presence betrayed only by gravitational influence. Others drift alone, far from anything, their light too dim to register. They do not move quickly. They do not change in any way that would catch your attention. They simply exist, radiating their heat into the void, degree by degree, eon by eon, waiting for a future so distant it might as well be infinite. In theory, if you wait long enough, the white dwarf becomes something else entirely. A black dwarf. A black dwarf is the final stage, the end of the line. A cold, dark crystal of carbon and oxygen, drifting invisibly through space. No light, no heat, no fusion, no radiation, no energy of any kind. Just matter, arranged in a lattice, held together by electron degeneracy pressure, inert and silent and invisible. It would be the corpse of a star in the truest sense. Not dying, dead. But here is the thing. No black dwarf exists anywhere in the universe today. Not one. Not in our galaxy, not in any galaxy we have ever observed. The universe is not old enough. Not even close. The cooling timescale required for a white dwarf to become a black dwarf is at least 100 million billion years. That is 10 to the power of 17. A 1 followed by 17 zeros. The current age of the universe, by comparison, is less than 14 billion years. The white dwarf would need to cool for more than 7 million times longer than the universe has existed. So the black dwarf remains, for now, a hypothesis. A prediction. A sketch of what the far future might hold, if the laws of physics continue to operate as we understand them, if the universe expands forever, if nothing intervenes. We do not know what will happen in 100 million billion years. We do not know if proton decay will dissolve matter itself, long before that. We do not know how dark energy will shape the expansion, or whether the fabric of space-time will remain stable. The timescales involved are so vast they dwarf not only human history, not only the history of life on Earth, but the entire history of stars themselves. And yet the white dwarfs wait. They are waiting now. Scattered through every galaxy, cooling in silence, invisible, unless you look in just the right wavelength at just the right moment. Some of them were once stars like the Sun. Some were larger, some smaller. Some died as planetary nebulae, their outer layers cast off in glowing shells that lit the surrounding space for 50,000 years before dispersing. Others simply shed their envelopes in quiet stellar winds. No fanfare, just a slow unraveling. But all of them arrived at the same place. A white dwarf. A cooling ember. A star that has run out of ways to fight gravity and has settled into a final, stable configuration that will last longer than anything else in the universe. They do not explode. They do not collapse into neutron stars or black holes. They are not massive enough for that. They simply cool. And cool. And cool. If physics holds as we understand it, the white dwarfs that exist today will one day become black dwarfs. They will cool completely. They will stop radiating. They will become dark, invisible relics, drifting through a universe that has long since exhausted its supply of hydrogen, long since ceased forming new stars, long since gone dark itself. But that universe is not this one. That future is not our future, not in any time frame that connects to the present. The stars you see tonight, the white dwarfs cooling in the halo, the sun that will one day join them, all of them exist in a universe that is still young, still bright, still full of hydrogen clouds and star formation, and galaxies colliding, and light traveling across billions of light years to reach your eyes. The white dwarfs are patient. They have no choice. They will keep cooling, keep fading, keep waiting, long after everything else has changed, long after the last star has formed, long after the last planet has frozen or evaporated, long after the galaxies themselves have drifted so far apart that the night sky goes black. And even then, they will not be black dwarfs. Not yet. They are the stars that wait, the embers of a universe that once burned brightly, quiet now, dim now, but still here, still warm, still giving off the last remnants of the fire that once held them together. And they will go on waiting, in silence, in darkness, for a future so far away that no clock we have can measure it. Every point of light you have ever seen in the night sky is a fire. Some are young, some are old, some have already gone out, and their light is still traveling toward you. The star that made the carbon in your lungs burned for millions of years, and then gave everything it had back to the universe. So that eventually here in this room, in this breath, it could be again. The universe does not waste anything. It only transforms. A nebula collapses. Gravity pulls inward on a cloud of gas and dust hundreds of light years across. The material compresses. Temperature rises. A protostar forms at the center, glowing faintly in the infrared. invisible to human eyes but radiating heat into the surrounding cocoon. When the core reaches millions of degrees, hydrogen atoms begin to fuse into helium. The protostar ignites. A new star is born. For billions of years, it burns. Hydrogen fuses into helium in the core, releasing energy that creates outward pressure, balancing the inward pull of gravity. Two forces locked in equilibrium. The star simply burns, steady and bright, a point of white light against the dark. Then the fuel runs out. The hydrogen at the center is exhausted. Fusion stops in the core and begins in a shell around it. The core contracts. The outer layers, flooded with heat from below, expand. The star swells. What was once a point of white light becomes a vast red cloud, its surface cooling and reddening as its radius grows to swallow the inner planets. Mercury will be engulfed. Venus will be engulfed. And likely Earth as well, though the details are still debated. For stars like the Sun, the outer layers drift away in strong stellar winds, expelled into space as a glowing shell of gas. The remaining core ionizes the expelled material, causing it to glow. A planetary nebula, one of the most beautiful structures in the cosmos. Blues and greens and reds stretched across light years, lit from within by the dying core at its center. The name is a misnomer. Early astronomers thought they resembled planets seen through small telescopes. They are nothing of the sort. The nebula lasts only about 50,000 years, brief by cosmic standards. Then the gas disperses, mixing with the interstellar medium. And at the center, what remains is the core. A sphere, roughly the size of the Earth, but with the mass of the Sun compressed into it. A white dwarf. Matter so dense that a single cubic centimeter weighs roughly a ton. It is composed primarily of carbon and oxygen, the ashes of helium fusion, packed into a crystalline lattice held up by quantum pressure. The white dwarf has no fuel left. Only heat. And heat eventually leaves. For more massive stars, the end is not quiet. A star born with 10, 20, 30 times the mass of the Sun burns hotter and faster, fusing progressively heavier elements in its core. Helium into carbon, carbon into oxygen, oxygen into neon, silicon into iron. Each stage releases less energy than the last. And then the core fills with iron. Iron is where fusion ends. Fusing iron consumes energy rather than releasing it. The core can no longer support itself. Fusion stops. The core collapses in fractions of a second. The outer layers rebound in a catastrophic explosion. A core collapse supernova. For a few days, a single dying star can outshine every other star in its galaxy combined. What is left depends on the mass of what remains. A lighter core freezes into a neutron star, matter so dense that a sugar cube would weigh 1 billion tons. A heavier core collapses further still, past any known stopping point. A black hole. Every stage of this cycle releases material back into space. Carbon, oxygen, calcium, iron, elements heavier than iron, forged in the neutron-rich environments of supernova explosions and neutron star mergers. The raw ingredients for the next generation of stars, the next generation of planets, the next generation of life. You are one of those transformations. The oxygen you are breathing right now was fused in the core of a star that died before the Sun was born. The calcium in your bones was forged in advanced stellar burning stages and dispersed by a supernova explosion. The iron in your blood passed through the interior of a massive star in its final moments. Every atom heavier than hydrogen in your body has a stellar history. A lineage that stretches back through generations of stars, each one living, dying, and giving its material forward. This is not metaphor. This is the way the universe builds complexity from simplicity. The white dwarfs cooling in the darkness tonight will take billions of years to fade. The oldest known white dwarfs, 11 to 13 billion years old, have cooled to temperatures around 4,000 degrees. Still hot by human standards, still glowing faintly in the infrared, they will continue to cool for trillions of years more. In theory, a white dwarf will eventually become a black dwarf, a cold, dark crystal of carbon and oxygen, drifting invisibly through space. But the cooling timescale required is at least 100 million billion years. The universe is not old enough yet, not even close. No black dwarf exists anywhere in the cosmos today. The fires are still burning, the light is still traveling, and the cycle continues. Somewhere in the Milky Way tonight, a cloud of gas is collapsing under its own gravity. In a few 100,000 years, it will ignite. A new star will be born from the remnants of old ones, and the atoms that once belonged to a red giant, or a supernova, or a planetary nebula, will find themselves inside a new core, fusing into new elements, beginning the process again. Nothing is wasted, everything continues. You are not separate from the cosmos, you are part of it, you are one of its transformations. The star that made you burned for millions of years, it expanded, it shed its outer layers, it collapsed, it exploded, and the atoms it released drifted through space for billions of years, until they found themselves inside a new nebula, a new solar system, a new planet, and eventually, here. Rest now, the stars will keep burning. Every star in the night sky is keeping time toward its own end. The Sun, the ordinary yellow star that holds this world in its orbit, is approximately 4.5 billion years old. It has been burning hydrogen in its core for all that time, and it will continue to burn for roughly another 5 billion years. Then the fuel will run out, and the Sun will die. This is not a tragedy, this is a schedule. Every star you see tonight is somewhere on that same arc. Some are young, still gathering themselves from the clouds that made them. Some are old, swollen and red, their cores already cold. A few have already died, and their light is still crossing the void toward you. The way each one dies depends on a single variable: mass. And the process that kills them is the same process that forged the atoms in your blood and bones. Lower the lights. Put on your headphones. A star begins as a cloud of gas and dust, hundreds of light years across, drifting through the dark. Most of the cloud is hydrogen. For millions of years, nothing happens. Then, somewhere in the cloud, a slight compression occurs. Gravity takes hold. The cloud begins to collapse. At first, the collapse is slow, but gravity is patient. The cloud pulls inward, contracting under its own weight. As it shrinks, it spins faster. The material at the center compresses, and compression generates heat. After 100,000 years, the core is glowing. This is a protostar, not yet a star. It has no fusion. It has only gravity and heat. The collapse continues. Millions of years pass. The core grows hotter. And then, when the temperature at the center reaches roughly 10 million degrees, hydrogen nuclei begin to move fast enough to overcome their mutual repulsion. They collide. They fuse. Hydrogen becomes helium, and in the process, a tiny fraction of mass converts into energy. The reaction releases pressure, outward pressure, enough to push back against gravity. The collapse stops. The star ignites. For billions of years, two forces hold the star in perfect balance. Gravity pulls inward, trying to crush the core, Fusion pushes outward, trying to blow the star apart. Neither wins. The star simply burns. This is the main sequence, the long middle of a star's life. It is stable, it is predictable. The Sun is in this phase now, and has been for the last 4.5 billion years. How long a star remains on the main sequence depends entirely on its mass. A star born with 30 times the mass of the Sun burns hotter and faster, racing through its fuel in only a few million years. A red dwarf, born with a fraction of the Sun's mass, burns so slowly it can last hundreds of billions of years, longer than the universe has existed so far. The Sun, a middling yellow star, will spend roughly 10 billion years on the main sequence. It is about halfway through. But eventually the hydrogen runs out. The core, for the first time in billions of years, goes quiet. Fusion stops. There is no outward pressure to hold back gravity. The core contracts, and as it contracts, it heats. The temperature rises high enough that hydrogen in a shell surrounding the core begins to fuse. The fusion migrates outward. The energy from that shell floods into the outer layers of the star, and those layers expand. The star swells. What was once a point of white light becomes a vast red cloud, hundreds of times wider than it was before. The surface cools as it stretches, shifting from white to orange to deep red. This is a red giant. The Sun will become one in approximately 5 billion years. When it does, its radius will grow to somewhere between the orbit of Earth and the orbit of Mars. Mercury will be swallowed. Venus will follow. Whether Earth survives depends on a race between the Sun's expansion and the outward drift of Earth's orbit as the Sun loses mass. The models do not agree. What they do agree on is this. Long before the Sun's surface reaches Earth's orbit, the oceans will be gone. The atmosphere will have been stripped away. Life, if any remains, will have ended billions of years earlier. The red giant phase is brief by stellar standards. For a star like the Sun, it lasts only a few 100 million years. The helium core continues to contract and heat until it reaches 100 million degrees. At that temperature, helium itself begins to fuse, forming carbon and oxygen. The star stabilizes for a time. But helium burns faster than hydrogen. The fuel is spent quickly. And then the core goes cold again. For stars of the Sun's mass, there is no next stage of fusion. The core is not hot enough to ignite carbon. Fusion stops. The outer layers begin to drift away. Strong stellar winds blow the envelope of the star outward into space, leaving behind only the hot, dense core. That core, still radiating ultraviolet light, ionizes the expanding shell of gas around it. The gas glows. This is a planetary nebula, one of the most beautiful structures in the cosmos. Blues and greens and reds, stretched across light years, lit from within by the dying core at the center. They were named for their resemblance to planets seen through early telescopes. They are nothing of the sort. A planetary nebula lasts only about 50,000 years. Then the gas disperses into space, joining the clouds from which new stars will one day form. What remains is the core, a sphere roughly the size of Earth, but with a mass close to that of the Sun compressed into it. This is a white dwarf. The density is roughly a ton per cubic centimeter. A teaspoon of white dwarf material would weigh about as much as an elephant. The matter is so tightly packed that electrons are pressed into a quantum state that holds the star up against further collapse. The white dwarf has no fusion, it has no fuel. It has only heat, left over from the long ages of burning. And slowly, over billions of years, that heat radiates away. The Sun will end this way. In 5 billion years, it will shed roughly 40% of its mass and settle into a white dwarf of about 60% of a solar mass. It will glow faintly for a time, then dim, then cool. But stars born with more than about 8 to 10 times the mass of the Sun do not go quietly. A massive star burns hotter, faster and wilder. It fuses hydrogen into helium, then helium into carbon and oxygen, then carbon into neon and magnesium, then neon into oxygen and silicon. Each stage burns faster than the last. Silicon fusion lasts days, and at the end of silicon burning, the core fills with iron. Iron is where fusion ends. Fusing iron does not release energy, it consumes energy. There is no outward pressure. Gravity wins. The core, roughly the size of Earth and with a mass greater than the Sun, collapses in less than a second. Electrons are crushed into protons, forming neutrons. The core becomes a ball of neutrons, incompressibly dense. The collapse halts. And the outer layers of the star, still falling inward at a quarter of the speed of light, rebound off the core in a shockwave that tears the star apart. This is a core collapse supernova. For a few days, a single dying star can outshine every other star in its galaxy combined. The explosion releases as much energy as the Sun will emit over its entire 10 billion year lifetime, compressed into hours. And in that explosion, the star disperses everything it has made back into space. What is left depends on the mass of what remains. If the core is below about 2 to 3 times the mass of the Sun, it stabilizes as a neutron star, a sphere perhaps 20 kilometers across, composed almost entirely of neutrons packed so tightly that a sugar cube of the material would weigh 1 billion tons. If the core is heavier, the neutrons cannot hold. There is no known force that can stop the collapse. The core continues to shrink past any stopping point until it vanishes from the universe as we understand it. A black hole. The death of stars is not an ending. It is a continuation. The carbon in your body was fused in the core of a star that died before the Sun was born. The oxygen in your lungs, the calcium in your bones, the iron in your blood. Every atom heavier than hydrogen passed through the interior of a star. Some were made in the slow fusion of a red giant. Some were forged in the final seconds of a supernova. Some were created in the collision of 2 neutron stars, an event so violent it warps space-time itself. You are, in the most literal sense, made of dead stars. The atoms that form you have been recycled through multiple generations of stellar birth and death. They have been scattered across light years, gathered into clouds, compressed into new stars, fused into heavier elements and scattered again. And at some point in that long history, a particular collection of atoms came together to form you. Nothing is wasted, everything continues. The white dwarf left behind by the Sun will not remain hot forever, it will cool, slowly. A white dwarf takes billions of years to drop from tens of thousands of degrees to a few thousand. The oldest known white dwarfs, formed roughly 11 to 13 billion years ago, have cooled to temperatures around 4,000 degrees. They are still glowing faintly, still radiating the last of their heat into the void. In theory, a white dwarf will eventually cool completely. It will become a black dwarf, a cold, dark sphere of carbon and oxygen, emitting no light, no heat, no radiation of any kind. Just a crystalline remnant, drifting silently through space. But the cooling timescale required is at least 100 million billion years, tens of thousands of times longer than the current age of the universe. No black dwarf exists anywhere in the cosmos today. The universe is not old enough. Not even close. Every point of light you have ever seen in the night sky is a fire. Some are young. Some are old. Some have already gone out, and their light is still traveling toward you. The star that made the iron in your blood burned for millions of years, and then gave everything it had back to the universe. so that eventually here in this moment it could be you. The universe does not waste anything, it only transforms, and tonight you are one of its transformations. Rest now. The stars will keep their time without you. You travel tonight through the full arc of a star's life. From the slow collapse of a cloud to the moment a white dwarf stops glowing. From the quiet death of something like the sun, to the violent end of something 30 times its mass. Every atom heavier than hydrogen in your body passed through at least one of those deaths. The stars that made you are gone. But you are here. Some of you are still awake. Some of you drifted off hours ago. Either way, the dark will still be here. So will I. Wherever you are tonight, under city light or open sky, you are standing inside the debris field of stars that died before the sun ignited. Rest in that. Tomorrow night we'll be here again. Same sky, different story.